So we'll have a couple more days of kind of hybrid teaching until everybody's able to be back in class. So I guess bear with me and I'll write on the screen instead of the board. What I wanted to start with today is just kind of the brief overview introduction of how the course is run and what to expect. Again, hopefully this is familiar to a lot of you, but just so that I actually run through some of this stuff. So I'm on the course Moodle page right now. So like it was in Thermo, the course is going to be organized on the Moodle page by week, where you'll have, you can see there's some stuff here. I have some videos that we watched last week if you want to go back and find the links to those. There's also going to be a new video, a couple more that will show up. This is where if I hand out anything in class, this is where it will show up. If you missed something, you'll see what you missed, you know, that kind of stuff. And then we'll have a checklist of, sorry, we'll have a checklist of things that hopefully is the order that I would do them in. So as you're kind of going through things, check off where you currently are. I will try to keep it so that I'm updating Moodle and making it visible to you after we've had the class where that stuff is presented. So you check it Wednesday morning before class. There hopefully won't be any new stuff. It'll be only after class that actually the new stuff pops up. Yeah, so you can see there's going to be a homework. Kind of the typical cadence for the class will be homeworks on Fridays. So homeworks will be due hard copy in class on Fridays. New one will be assigned Friday for the next week. If you pull up the syllabus, I would encourage you to take at least a little bit of time in the next week or so and pull this up. We'll have help sessions for fluids on Wednesdays from 7 to 9 p.m. with Jack. That's not today, obviously, because we don't have anything that I think anybody should need to go to a help session about. So starting next week, though, we'll have help sessions on Wednesdays. I will also have office hours from 4 to 5 p.m., both Wednesdays and Thursdays throughout the semester. I think that those are going to be in Vanderwerf 222, which is the room across the way in Vanderwerf, right by the engineering department offices where we did the thermo help sessions. If that ends up getting rescheduled, I don't know, I might look for a room that we can actually book for the whole semester. But we'll at least do that in there tentatively. Otherwise, if those times don't work, I'm always available over email and we can meet. You can meet in my office, or we can set up a time over email to be able to meet to talk about something, whether it's homework or tests or life or whatever it is. My office is in Scott 2106, so not by the other engineering faculty. I'm kind of by the chemistry folks. Our textbook, you should have got there's a virtual textbook that goes with the course. I know I had a couple of people talk to me about old editions, like the 9th edition, if you wanted a hardcover. I think that's the last one where they actually printed a hardcover, which is a little sad to me. But if you have the 9th edition, you can certainly use that for the class. It's going to mismatch homework problems in some places. So you might want to check if I assign problem 8.61, you might want to check with somebody before you do 8.61 in your older edition book. That's really the only major thing. Basically, the reason we're not using that is because they don't sell it anymore and they only do the virtual one. So that's what we're stuck with. Grading is going to be like it was in thermo. I'm going to attempt to have something like 1,000 points in the class. What that will mean practically is that if you just calculate your raw percentage, you will be close-ish to what the actual raw percentage is. It's not going to be perfect because I'm not going to get the point totals exactly right. So I use the percent weightings, but it will be close enough that you don't need to go through the actual calculation and do it by percents. It'll be close. I think usually by the end of the semester, the difference between people's adjusted weighted scores by the percentages and like just raw point totals, nobody's ever more than like a 0.5% different between those two. So it's going to be close to what your percentage is. So hopefully that makes it easy if you're kind of trying to keep up along the way. Hopefully it helps keep that easy. The homework sets, I do not require kind of specific formatting, so not engineering paper. That said, I have specific guidelines here that I would like you to take into account. They're the same guidelines that we used in Thermo, although I think I would say that they were followed with varying degrees of exactitude. A new page for each problem. So if it's a really short problem that takes like 1/4 of the page, then okay, you can fit 2 problems on 1 page. That's not, but give yourself space is kind of the key point. Nobody gets an award. There are no medals handed out at the end of the semester for you used the least sheets of paper for your homework. That's not an award that we're going to give out. Work problems clearly in a step-by-step manner. I would say a pretty significant part of working in teams is communicating clearly. You will be engineers. You will be working in teams with other engineers, communicating technical stuff, learning how to do that clearly to other people, show them what you did, what your assumptions were, what you were thinking, how you did it. That's part of how you communicate in teams of other engineers. Homework is like baby steps to practicing how to do that well. So there's a lot of stuff that goes into communicating well in teams and working in teams. Being able to communicate, show stuff, show what you're thinking, show what your assumptions are, those kinds of things are important. So that's why I'm going to make you, probably at least early in the semester, be going through myself and asking the grader to go through and really kind of hammer on that a little bit more than what we did even in Thermo. Give units for all answers. Numbers without units are sad. Use an appropriate amount of significant digits, right? If you're a runner and somebody asks you what your mile time is, nobody says, I ran the mile in 7 minutes, 30 seconds, and 12 hundredths of a second, because that's ridiculous. So use the correct amount of sig figs. Usually that's about 3, 2, 4, 3, somewhere in there. Usually it's not 12 unless you're like actually doing things that require 12 sig figs. But usually if you're doing things that require 12 sig figs, you know that you're doing something that requires 12 sig figs. So think about it like, imagine somebody, you're baking in the oven and your mom asks you what to set the oven to, and you're like 376.427. Like just 375, set the oven to 375, right? Use like normal people rounding for final answers. That doesn't mean you necessarily round all the way through, because that can give rounding errors. But final answers, right? This is again part of communicating in a reasonable manner. If your boss asks you what temperature to set the oven to and you say 376.4927, your boss will look at you funny. So hopefully we will teach you not to do that. Exams, we're going to have 3 exams. We're going to have participation assignments that feel kind of like what they did in Thermo. In addition to the exams, we'll have a couple quizzes. The quizzes will be announced before they're given. They're going to be short at the beginning of class, kind of like what we did in Thermo. The exams are going to be on the dates that are in the course schedule. So if you want to go and look through and see when our exams are going to be, you can do that already. I will not change these dates unless there is a mass outcry for some reason why we should change the dates. If there is, then I can change the date. But otherwise, I will not change the date on you. So unless you want me to. You can see also on the right, kind of an idea of what topics we're going to be covering and what chapters they're in. We are going through this book fairly linearly. We skip around a little bit, but not too much. So instead of like 7, 8, 9, we do 8, 7, 9. we'll see how much we get to after that. But we're going to go through fairly linearly. We're not going to cover everything that's in the book, but it's going to be a good resource. I would like scan through the topics and stuff that are in there, especially as you're doing homework, to kind of remind yourself what we talked about in lecture. You can read things a little bit different way than I explained it. It's going to hopefully a good resource for you. The sections, like the stuff on the right, the topics that we're going to cover, I probably will get a little bit off track and not cover those exactly on the dates that I said. So if I do, obviously, you know, what's said there, exam 2 is going to be on chapter 4 and 5. It will be on chapter 4 and 5, but maybe only like part of 5 because we didn't cover as much of it as I wanted or something like that. I'll let you know when we're actually studying for the exams. So don't take like on March 13, we're going to do developed flow and turbulent flow in pipes. Maybe we will, but maybe that ends up getting pushed like a day back or a day forward or something like that. So those might bounce around a little bit, hopefully not too much as we're going. Okay, you will also see some dates. So here on March 15 at the bottom there, and on April 14, you'll see stuff about a report. It's going to be kind of like a group homework thing that will take the place of most of our homework during that section. When we get to it, I'll lay out what it is and what you're going to be doing and stuff, but those dates are on there as well. That it's a report / project. So you're going to be doing an analysis and writing up a report on it. So, but we'll get to that when we actually get to that. Yeah, other than that, like final exam dates and stuff are already on the syllabus. So if you want to know when those are going to be, they're there. Just, yeah, give it kind of a quick read. It doesn't need to be totally complete, but can hopefully 3 weeks from now, when you forget things, you can go back and find it there. So that will just live up at the top of our Moodle page. Any general questions? Hopefully none of that is overly surprising. Okay. And if there are issues or questions that come up, obviously feel free to ask me. Okay, so did I lose that? All right, so what we're going to start with today. No, don't do that. Duplicate. Okay, good. So we're going to start with our, I'm going to post these slides as well on Moodle. I think they're actually already posted. I don't know if I made them visible yet, but I'm going to post these slides on Moodle. We're going to just cover 3 basic concepts. I wanted to make them in slide form rather than me just writing it out because some of it's a lot of words. And some of it like this is pictures that are maybe easier to visualize if it's drawn better than me just scribbling it. So 3 concepts around fluids that are going to be important, that are going to live with us for the rest of the semester. So these are going to be relatively important, especially the first 2. So the first one is the definition of a fluid. So this is fluids class, so learning what a fluid is. We all kind of know. A fluid is a substance that deforms continuously. So if you write nothing else, write that little snippet, something that deforms continuously. So that means when you apply a stress to it, right, like a shear stress, if I try to take a solid object and, you know, rub my hand over top of it or stretch it from the top and bottom, it might deform a little bit like what's shown on the left. But it's at least up to a certain point. Once that force is no longer applied, it will come back to its original shape. So that would be a solid. That's an elastic deformation where you would deform, but then you come back to the original shape. That's solid behavior, elastic behavior. As you've learned in materials class, there's some point where solids fail and they actually yield to that type of a shear stress. But in the elastic regime where solids are behaving happily, you can apply that stress, they won't yield, and they'll come back to their original shape. Fluids, when you apply any force of any magnitude, they are going to deform continuously. So if you push with any force on water, it will flow in response to that movement. So that would be kind of a classic fluid. So something like shaving cream is not exactly a perfect fluid because it does not deform continuously under any stress, right? If you push on it really, really soft, it will behave elastically. It will behave like a solid. And if you push on it just a tiny bit harder, then it will start to actually deform continuously and flow. But like a classic fluid, a perfect fluid, what we'll eventually call a Newtonian fluid after Isaac Newton, a Newtonian fluid will deform continuously upon the application of any stress or any force. Okay, next one. This is going to be kind of an important one. Hopefully the last one, you're nodding your head because that makes sense. This one is going to be one that's a little weird, probably. Doesn't look like my link works, so I'll copy and paste it. This is the no slip condition. So the no slip condition, rather than just telling you about it, I figured I would show you.
Massive readings.
After we apparently watched Star Trek. So this is the no slip condition. So what's happening here, we're going to take food coloring in water, and we're going to put a drop of food coloring at the bottom of like a fish tank. The water is flowing from right to left. You'll be able to see that. And watch what happens to the food coloring that's right on the bottom surface of the tank. So you can see the fluid flowing. It's flowing actually relatively fast. The stuff that they put at the bottom of the tank isn't moving at all, though. That's the no slip condition. It's not stuck there. As you see, you brush it a little bit and it flows. It was not like sticky to the bottom, but it is sticky to the bottom because of the no slip condition. So no slip, it means between a fluid surface, and a solid surface, between a fluid and a solid, the fluid is going to be stuck and not slip along that solid surface. So if you have, for example, a car driving down the highway, the air right in contact with the car is moving exactly at the speed of the car. It's moving along with your car. The air that's just a little ways away is moving at a different speed, right? The air that's really far away is maybe not moving at all, or moving at whatever the normal wind is moving at. But right on that, attached to the surface, we don't have slip, where that fluid like slides and slips along the surface. The velocities are exactly matched there. That's going to be a really important condition when we actually start to look at the shapes of different flows. When we look at aerodynamics, the no slip condition is going to come up a lot when we look at how fluids and solids are interacting. But yeah, maybe kind of I don't know, probably one that you've never thought about what's actually happening at the interface between a solid and a fluid. So that's true for gases. It's also true for liquids. Okay, the last one, and this I would say is maybe the one that we won't come back to too much, but we will a little bit. We talked a little bit in thermodynamics about compressibility. We're going to make some of the same assumptions. Liquids are practically incompressible. It means they're not squishy. If you press on a liquid, it doesn't really expand and contract that much. Gases, on the other hand, are typically compressible. So they change as you press on them. They change. Like we can do something like the ideal gas law to be able to look at what that looks like. The other difference between liquids and gases are liquids have a definite volume, so you can like put it in a container and there will be a free surface, like a top to that liquid. Where a gas, if you put it in a container, it will expand and just fill up the whole room. or the whole world, right? It'll keep expanding. It won't ever stop until it fills up everything, all portions of the vessel. So that's kind of a functional difference. Practically, a lot of the things that we're going to end up doing are going to be, I mean, it'll be pretty obvious when we're talking about gases and liquids, and you guys are familiar enough with gases and liquids and how they behave. Most of the time, it won't be an issue. The one kind of thing, the compressibility, we'll have to get into that a little bit when we start talking about gas flows, and when we can think that it's not, and when we have to care about the compressibility of gases. So gases will be a little bit weird because they can expand and contract when you press on them. Okay, so those are three key topics. Just kind of ideas about fluids. The next thing that we have to cover as we're kind of getting, building up our vocabulary, building up how we can talk about some of this stuff, we have to start talking about how to describe fluid motion. So that's going to be our next thing. And this I will, so if you want to write this, the heading of this topic will be fluid motion. So there are going to have to be lots of different ways that we talk about fluid motion, because we're going to be looking at how do experiments talk about fluid motion, how can we use calculations to talk about fluid motion. Fluids can go all sorts of different ways, so we're going to have to start using vectors and all sorts of fun things to be able to put all of this stuff together. So how can we talk about, how can we visualize, and how can we do math with fluid motion? All right, so we'll call this part fluid motion. So in general, fluids are, right, not always stationary. We'll deal with when they are, but if they're moving, we can describe the movement by a velocity field. So what do we mean by that? So if we have something like this, we have coordinates x, y, z. This fluid particle P1, we could describe its movement at a given time. So this is at time t. P1 is right there and it's moving that way. And I don't know, we'll say P2 is right here, some other particle, and it's moving, let's make it move really slow. So it's moving slowly down. So particle 1, that little bit of fluid has that velocity. Particle 2, that little bit of fluid has a different velocity. It's going a different direction. We can then look at it a little bit later. So at time t plus dt, some amount of time later. Okay, let's say, so P1, maybe it's moved to here, P1. And now its velocity has changed. We'll call this V1 prime and P1 prime. A little bit later. So it moved a little bit, but the velocity changed. Now it's going in a different direction. P2, let's say this is P2 prime. Now it's sped up a lot. And it's going faster. So velocity fields are going to be complicated. They're going to be, every particle will have its own separate velocity. That velocity is changing with time. It also could be changing with position. If you imagine like you're a particle that's flowing out of a hose, right? When you're in the hose, you're maybe going one speed, and as you go out of the hose, you start to actually fall to the ground. So you're then changing direction, and maybe you're changing speed. Maybe you're going through a nozzle and getting sprayed somewhere. So you might change speed with position or with time. So it's going to be complicated. So we have to use, in general, 3 dimensions to describe it, as well as time. So in general, we're going to use we're going to describe the velocity fields in their individual components. So the velocity field, I'll write this and then write some notes on it, equals W K hat. So this is that's the velocity field. U is the X component. V is the Y component. W is the Z component. So we're going to split our vectors, which are, pointing in all different directions. We're going to split them up into how much is it pointing in X, how much Y, how much Z. And then these are I, J, and K are the unit vectors, right? The X, Y, Z unit vectors. Okay, and in general, U, so how fast we're going in the X direction is going to be a function of our X position, our Y position, our Z position, and T. How fast we're going in the Y direction is going to be a function of position and time. How fast we're going in the Z direction is going to be a function of all of our spatial variables and time. So to summarize this, so our velocity field is going to have to depend on both space and time. And this is what's going to make fluids a little bit tricky, especially as we start to look at things that are happening and changing maybe with time. Okay, so we can look at different examples. We could look at a velocity field, which is 2x squared y I hat plus 3t k hat. Okay, so we have, this would be kind of a weird velocity field. We would have to plot it to actually be able to see what this looks like. There are going to be lots of velocity fields that we're going to write equations sort of like this that would describe something like fluid flowing against a flat wall, or fluid flowing down the length of a pipe, or flowing through a cone. We can actually write equations like this that describe fluid flowing in a corner. What does that look like? We can write equations like this that would describe that. This one, we would have movement in the X and Z directions. So when we're looking at these, the little vectors, I hat, K hat, that tells us which direction the vector is pointing. So that tells us which way we're moving. So we're moving in the X and Z direction. There is no movement, there's no flow in Y for this vector field. But our speed changes in X, Y, and with time. Okay, so what does that mean? So that means we're pointed in, say, X and Z, maybe like that. But as we go this way, we maybe get faster or slower. So we're not pointing that way, but as we move in the Y direction, we would get either faster or slower, depending on which way we move. So you can have flows that are, and this is why it's going to be a little tricky. There'll be some practice problems in the homework to try to help you unwrap this, but how we talk about the vectors, which direction is the thing pointing in, which way is it changing, right? If you have wind blowing across the ground, say, really high up, the wind is fast, really close to the ground, the wind is slow, but the wind is not pointing toward the ground. So it would be changing vertically, but not pointing vertically. It might be pointing kind of in like one of these directions, but it's changing in the up and down direction. So we're going to use that kind of language quite a bit as we're describing flows. Which way is it pointing? In which directions is the velocity changing? Those can be the same thing. Those can be different things. Okay, we also have to talk about how to visualize flow. Okay, there are going to be three different kind of ways that we could do, say, like an experiment to be able to visualize flow. Flow visualization experiments like the video we just watched of, food coloring in a liquid, those are really common experiments to try to look at what fluids are doing. But those don't directly give you any information about what the velocity field looks like. So you're going to be able to visually see what's going on, but you're not going to be able to get an equation like the one at the top of the page, basically. So we're going to have to find ways to kind of mash what we're seeing to velocity fields and back and forth between the two so we can start to visualize what these things look like. The first tool that we're going to use is all one word, a timeline. This is a line through adjacent particles. That show relative motion over time. So we're going to watch flow visualizations where, say, like every second, a string of bubbles is released, and then you watch where those bubbles go. And they can show you like the bubbles on the outside are going slow and the bubbles in the middle are going fast. And every so often they release a new set of bubbles. We'll watch experiments like that. Those would be timelines. To draw kind of a quick picture, if we imagine we have a solid surface that's moving this way and another solid surface down here, which is not moving, the no slip condition will tell us that the fluids at those surfaces have to be going the same speed as the surface. And what we'll learn is you get a linear velocity profile in between those two plates. You have two parallel plates, like one thing sliding over another. You get a linear velocity distribution between those. So with timelines, you would see that something like this. This would be time equals 0, T1, T2, T3. So you would have these individual lines that show the relative fluid motion, and you can kind of back out then what's happening with velocity. The ones at the top move farther, so it's a higher velocity, but it's not like directly showing you velocity field. It's giving you information about it. Second one, are path lines. So a path line, this is the path or trajectory of an individual fluid particle. Okay, so essentially what we're doing is we're trying to watch, like, imagine a long exposure of car headlights. You're watching the entire path that car traveled. So you're watching an individual car, the path that it is traveling. Another, right, if you're like, right, let's draw a football team. If we want to look at like the route that an individual receiver runs, it's not really telling you about the velocity of that receiver or that individual fluid particle, but it is telling you the path line, the path that they're traveling. Okay, so you could imagine, right, how would we visualize this? You could put a piece of chalk inside of our fluid and you can watch where that travels and you can visually see it. Or you could put some sort of marker tracer in the fluid and you can watch how that moves and you can track that motion with time, for example. And you could look at then the path line, the path that fluid traveled. That can give you information about what the flow looks like, what it's doing, what's happening. All right, last one is a streak line. So timeline, path line, streak line. This is a line of connecting particles that flow all from a specific point. So the kind of classic example for this when we watch dye being released into the flow, it's all being released at the same point, and you see it wherever that fluid ends up traveling. And if there are changes in the fluid and the changes, right, then maybe it ends up going a different direction at some point. If you imagine, okay, so how are these things different? If you imagine you're a person, right, and you have this is a great drawing. So you're holding a garden hose. And you're shaking this garden hose up and down. What's going to happen to the water as it comes out of the garden hose? Right, you're just vibrating it up and down a little bit. It's going to kind of change velocity a little bit. And what's going to happen is you're going to end up with a water that looks like that until it hits the ground, right? But if you were to look at any individual particle of water, it travels on a parabolic path. It's only because you're changing the velocity that it looks like a squiggly thing. So this would be the streak line. If we wanted to look at the path line, for example, the path of an individual particle, it would still look like this. Right, that would be one path line. And there would be another path line down there and another one in the middle, because each individual particle still is following a parabolic path. So you can see maybe how these things can be different. Now, if I were to just hold the hose and not be shaking it, then they become the same thing. So for a lot of these things, we have differences when we have when we have things changing with time. If things are not changing with time, some of the stuff starts to converge. But all of these are different techniques that we can use. We can do experiments to actually use them to visualize fluid flow. We'll look at videos throughout the semester of all of these different techniques. The last one, which is one that we're really interested in, but don't have direct ways of visualizing, is called a streamline. So we have these three things that we can do experiments, we can visualize, and this one thing that we want, but we don't have opportunities to visualize. Streamlines have two parts to them. The streamlines are tangent to the velocity field. And kind of another way of saying that is velocity perpendicular to streamline is 0. So it's exactly equal to 0 perpendicular because it's tangent. That's saying the same thing. So what a streamline would be, if we had a streamline that did, say, something like this, at any given point, streamlines aren't going to tell us the magnitude. They're not going to tell us speed. They're only going to tell us direction. So this would be like the direction at that instant. At this instant here, the direction is, again, tangent to the velocity field. Over here, again, tangent to the velocity field. So this is our streamline. This is a vector from our velocity field. So streamlines are going to be kind of one of the best tools that we can use to try to describe the velocity at every different point. Right, by drawing a line that's tangent to the velocity at every point, you can kind of see the curve, the shape of the velocity field. Okay, so we're going to do a short, and it's going to be, I guess, kind of really short. We'll get started on it and do most of it. You all received a email from me during class. Pull out your phones and open the video link on that and watch that video. You might want the sound on. I'll be passing this out while you're watching that. It's another Don Pettit video because I like him. You're going to be watching him do an experiment, and then you're going to try to look at that experiment and draw your own path lines and streak lines and streamlines. But you're going to listen to it because then you can actually see what's going on. He's holding basically a coat hanger that's wrapped into a loop that has like a two-dimensional film of fluid in, and he's mixing it up.